Okay, so we're going to switch gears just a bit today. It's the last section of the semester. It's kind of 7-8, but we're not going to just stay in 7-8. It's kind of custom. I've tried to trick this one out, you know. If you guys remember at the beginning of the year, we started working with real-world data, or just working with data. I don't think we're seeing a lot of real-world data still in this class. It's kind of made nicer for you still most of the time. Not always, but most of the time I think it's still kind of nicer, right? But we worked with modeling data. The only kind of function we tried to fit to a scatter plot, though, was what kind of function?
Linear.
Linear. So far, we're starting to learn some other functions, some other shapes, and I think the goal is, once we get by the end of this class, to be able to use any of those new functions, those new shapes, to fit data if it looks like it has one of those kind of shapes. Because before, if it had a curve in it, what do we do? We were just like,
Cry.
well, it's got a curve, it's obviously not a good model. Done. Now we have some curved functions to fit things like that. That's kind of the way you should think, okay? So I'll just write this down so you guys maybe you get lost later and come back to it. So I'm going to say recall. When you've got a scatter plot of data. Now notice, anytime you can make data into a scatter plot, how many variables are you working with?
Two.
Two. So you have like the x variable and the y variable, right? That's not always true. Sometimes you just have data where you have just like a bunch of numbers and it's just one variable. We'll look at those kinds of displays later, and you're not going to be able to use a scatter plot for that situation. We'll do that later this year though. If you have a scatter plot, you can try to make a model. That's our goal. One of the other big things besides the library of functions this year is we should be able to model real-world data. That's one of the uses of that library. So, does that mean that any situation possible in the real world, we're going to have like a nice elementary function we learned about this year to deal with it? I don't think so, but it turns out by the end of the year I think we'll have covered enough so that I think most situations where you collect data, we'll have a way to at least have an okay model that'll kind of fit them. So that's kind of crazy. By the end of this year, you should be able to model most real world data. That's kind of crazy. Not all. There's some that's a lot harder. You have to use more advanced techniques, but I think we have a lot. So what kind of functions do we have that we've learned about that we might model with?
The faces.
Once again, we did linear. What else?
Parabolic.
Yeah. I'm going to say quadratic, but that's perfect, Nick.
Exponential.
So if we see a U shape, that might be quadratic. I think now exponential. There's all kinds of things that are exponential. I think that's probably the most common model, maybe after linear.
Logarithmic.
Yeah.
Yeah, you got it right.
And we had some other shapes like our hyperbolas and stuff, but those aren't really functions, so we can't really use them for this kind of thing. Okay? Make sense? So let's just try an example. And you're going to need your calculator, so if you don't have that out, make sure you've got it. You can call this x and y or xf of x, same thing, right? Just different ways to think. So I'm going to start out with a very, very friendly data set. This data set should look eerily familiar. We'll scatter plot it. But before we even scatter plot it, what do you guys think? Let's try to think which one of those red models might be appropriate. Does it look like it goes up by the same amount every time?
No.
So it's not
Linear.
not linear, no way. Does it look like it's growing fast or slow?
Fast.
Fast. So which one of these grows slow? This grows at the same rate.
Exponential.
No,
Right?
Yeah, exponential grows fast. Which one grows slow? Think about the shapes.
Quadratic.
Oh, I think quadratic's still have the U shape. That's pretty fast. Logarithms look like this, right?
Yeah.
Logarithms have this kind of shape. That's a slow growth. I don't think that's going to work for this. We know it's got to be probably one of those two. Anybody know what this exact? This is perfect. This is a perfect scenario. Which one is it?
Quadratic. Exponential.
I hear quadratic. No. It is exponential. In fact, what's the model? You don't need your calculator for this. Don't these numbers look familiar? So those are power table numbers, right? What's this function?
Oh.
X
X
squared.
equals X squared. No, X, not X squared, X.
You know it's exponential.
Is it 2x? It's 2x. Yeah.
Isn't it that? That's not just a model, that is the perfect function to fit these, which is rarely ever going to happen, right? I'm using this example for a specific purpose, okay? So isn't that 2 to the x? 2 to the 0 is
Is it 1?
2 to the 1,
2, 4.
2 squared 4, 2 cubed 8, 2 fourths 16. That's exactly perfect, isn't it? Crazy. Let's scatter plot it though and see. So how do we know it's not quadratic? I mean, how do you know always? You know, you probably don't.
Don't actually know.
Okay, so review, where is this stuff?
That's not a problem.
Okay, where we go? This is something you need to know. Maybe we haven't done it enough this year yet. We'll keep doing it though. So stat.
Oh, I did this already.
Edit. There's your lists. Put your date in. Remember, you go up at the top, highlight it, and hit clear if you want to get rid of stuff that's there already. Are we all there? We all need to get to our lists. Hit statistic or stat, and then go edit. There it is. You're fine. We haven't done this enough yet, so right now it's okay if you can't remember. I think next time it's not going to be okay. Maybe still a little okay. Put your stuff in. So we've got X's. We'll put those in list 1. Put the Y's in list 2. Oh, I don't have that right. Gosh darn it. I put my Y's in. Weird. X's. There we go.
Why can't we just put in the function?
We could in this case.
But it won't let me do x up. Like, it won't let me do 2 root x or 2
Hold on.
power x.
What you need to be real careful of here is that your lists are the same size. If these dimensions don't match, your calculator can't do anything with those lists. It's a very common error. So if you ever get the error dimension mismatch, that's probably why. Okay, so always check real quick if they're the same. No. Good question.
How do you if you accidentally put in like one too many, how do you get rid of it?
Hit delete. If you want to delete one of these specific entries, you can hit delete. If you want to clear the list, you highlight the list and hit clear. Don't hit delete up here.
Why won't this let me put in x?
What do you want to put in? 2 to the list 1. Good question. That's just something we use a lot.
Someone over
that. Just freaks them out.
No. You don't need that. It's something I had for another class.
Okay.
There. Happy? Okay, scatter plot this. Make sure your plot is on, so go second quit. Scatter plot is under second y equals or stat plot. You need to remember where that is. hit enter, make sure it's on, so make sure that's bold. Make sure it's on a scatter plot. We're going to work with some of these later this year. And our stuff is in list 1, list 2. If you have yours in other lists, you can tell it which ones they're in. I like to use the big dot because I can see it better, but it's your choice. And then I go zoom. Now you could manually fix the window, but does someone remember what I hit zoom what if I have data? Standard is for functions.
Oh, it's 9.
It's 9.
If you go down, zoom statistic is for any kind of data you might have, any type of graph. And there we go. So now looking at that, just looking at the picture, because that's one of the ways we're going to decide in this lesson. What does it look like? Linear, quadratic, exponential, logarithm?
Looks exponential.
It looks exponential. It's kind of hard to say if this is a U shape. Maybe it, but see, it looks like if that was the vertex, it would start coming back up, not dropping down. So I think exponential is the best. And of course, we know it's perfect, right? Jake?
So, with the stat plot,
Yeah.
you just turn one on.
Yeah. I'll help you guys in a few minutes. I'm going through this example first, okay? All right. So let's pretend we didn't know that that was perfect. So I want to calculate the actual models and decide. So we need to use the picture, and there's one other thing we can check to see which one's best. Okay. So let's go stat back here. Instead of hit edit, go over to calculate.
Oh, they're static.
And then we wanted to check quadratic and exponential, right? Now which one of those things is quadratic?
5.
Yeah, quadratic regression. There's linear, there's cubic. We're not going to do cubic really. It's not very useful. Quadratic, we'll try that. Tell it what your lists are. List 1, comma. Comma is above the 7.
Oh, never mind. I see it.
List
I see
2. Those lists are on buttons 1 and 2 if you did second.
That's me too.
Huh?
And there you go.
Yeah, I got the same thing you did.
So
It's like set
Oh,
wrong.
calculate.
you're gonna just go.
Yours might look a little different, but yeah.
Shows up like this.
It's fine, just tell it. Calculate. It says list 1, list 2. Same thing too. Right. If you have a newer calculator, you might just have to scroll down to calculate. All right.
Just the center after that.
Yeah.
Now,
Okay.
which one of these things? Here's the model. Let's write down our model. So the model for quadratic is y equals, the one that would be equivalent to this is y equals 1.387 x squared, so that's a. And then b is negative, so minus 0.887 x plus, or excuse me, it should be minus, shouldn't it? Minus 0.25. There is the parabola that tries to fit this model. Now, if you wanted to see that, you could go put that in y equals and put it on the graph. What else do they give you? This is key. Remember, we had R before. R, you're going to get more into depth if you take a stats class in college or with me. R is a measure of the strength, remember? R is the correlation coefficient. It tells you how strong your model is. Is this R?
No.
This is R squared. So today we're going to learn what is R squared. You could take the square root to get R. Very nice.
0.3.
So here's what R squared is. This is key. We need to all have this down. So R squared is the percent. Notice it's a percent. So here we have 97.5% of variation. It's the percent of variation in the y's, these y's for our data set, right? That can be explained by whatever you did, whatever model you came up with. Let's say by the current model. So ours is quadratic right now. I'm going to say in there, excuse me. In the current model, by variation in the x's. So this model explains 97.5% of variation here by using those. But I thought we said this was our other model, exponential. And which one of them do you think is going to do better?
Exponential.
The exponential, because we said it's
Perfect.
perfect. So you guys tell me, what do you think r squared is going to be for the exponential model?
2? Oh.
Goes to 0?
0 is very weak. It's going to be 1. It's going to be like 100%. Remember, r is between -1 and 1, and so is like r squared. So I think for the exponential model, let's do it. So go back to stat calculate. Let's see if we get 1. Should be. So stat calculate. Now, do you guys see exponential? I don't, so let's scroll
is it
down.
and 0?
Another linear. There's the natural log regression, so if you want a log regression, there it is. Exponential, I think it's 0, yeah. We'll tell it just to be careful, list 1, list 2 again. And it says the model is y equals a is 1, b is 2 to the x. Look at that. Isn't that the same one?
Yes.
We just guessed it before. Do you think you're going to be able to guess it very often?
No.
No, that'd be hard stuff.
Yeah.
So it's y equals 2 to the x, and what's r squared? 1. That's perfect. So if you ever see that, you say, man, this is a perfect situation. Almost never going to happen.
I still hate how it doesn't have.
I'll fix that. Yours, you have to turn an option on. So okay. If you're not seeing r and r squared, let me know, and I'll help you turn that option on. All right. Let's do. I'm gonna have you guys try one other one while I kind of go around and do some calculator assistance. So try this data set. Okay, put that one. Put that one in your lists, and I want you to try different models. Make a scatter plot, look at a scatter plot, and then try some different models and see which one you want to decide on. I'll give you a few minutes and I'll help you out, okay? I'm also going to pass out a worksheet, so.
How do you clear the Mr. Reed?
Yeah.
How do you clear your tables?
You go up to the top and hit clear. You're in.
Wait, oh, hold on. I was zoomed in.
You were zoomed in the wrong way.
Just want to touch.
Start it off.
That turns out the tits are big. Do it up, son.
Calculator issues, let me know.
Oh, yeah. Did you almost like throw your calculator on the floor?
No, I don't press the whole button.
It's just
Destroy my math.
take that back. Yeah.
All right, cool, thank you.
This is totally. This is totally. Blackout.
Everybody get their scatter plot at least? So remember, when we go back to functions, and that scatter plot's still on, that's going to cause you a problem. So you're going to have to be able to go back and forth and turn it on and off. Okay.
I don't know what to do now.
So you've got your scatter plot. You go zoom 9 to scale it to the new data. It looks like that. I look at that and I say, does it have curvature?
Wait, that's first look like?
Go back to your data and look. Gotta be careful. Okay, so I say not linear, definitely it's got a curve, it's not a logarithm, it's growing too fast, it's either quadratic or exponential, so I'm going to try both. So I'm going to go statistic, calculate quadratic, list 1, list 2. And I'm just going to remember what my r squareds are. So r squared for the quadratic, so I'm going to use a subscript q, is 0.9998. Wow, that's almost perfect. Not quite. So close.
It wasn't closer with that.
You should not expect r squareds in the real world to usually be this high. They're not this good. They're like 0.8 usually at best. Anyway. And I'm going to try the exponential. Notice the reason that I picked these, I looked at the shape first. You need to look at the shape. When you do that one, you get r squared for the exponential is 0.9796. Which one's better?
The quadratic.
Quadratic's better. So I'm going to go back and get that model again. So make sure you have your quadratic up there. If you need help, let me know. I'll come look.
Do you want us to write down that AX version called BX?
Yes, we're going to write all that down on this problem. Okay.
I was like,
So we'll write r squared down in context maybe on the last one we do today. So let's just write down the model. So this time the model is y equals 0.9. It's just about, so you can put about here if you want. 0.9799x squared plus 0.0999x plus 2.071.
that's 4 decimal places.
And then if you like, you can go put that in your y equals to check. So you can go like this. What's up, Nick?
Is it alright if we go to 3 decimal places? So
That's the rule I've told you, so that would be great.
Because I went 0.9880 x squared plus 0.1
That's great.
x.
That's great.
Let's get this up.
So if you look at it, I don't think it's going through all the data points. It looks like it went through that one. It's slightly above here, slightly below here, but it's fitting them very nicely. Yeah.
Okay.
So there's the model we picked for that one. Let's do one more. Splodge book. Because I don't want to write all this down on the board. Let's look at example 2 in the book. I think it's kind of neat.
I forgot how to remember.
546.
7, 8. Yeah, 546.
Should it be a problem?
That one should be a parabola.
Why not do that one?
I think the exponential model worked very good on that one too. I mean, in the real world, you're usually really happy if you have r squared equals 0.9. I mean, that's for real. These are kind of fixed problems still. We're still not quite doing the whole full-blown thing like we would in stats. In stats, I mean, if we get r squared equals 0.8, we're really happy usually. It's pretty good. If you get r squared equals 0.4, then you're like, this is not going to work.
What page should we be on? 548.
Look at example 2. 546.
Yeah.
Okay, so example 2 is about diamonds. So we're trying to predict how much diamonds cost based on their weight. Let's just think about that situation to begin with. Do you guys think it's going to be linear? Like when a diamond gets twice as big, do you think it's going to always like be twice as much? What do you think is going to happen instead? If you have a diamond that's this big, it might be like $1,000 for a carat. I don't think this data is super accurate either. I deny. But a carat diamond, I got my wife two 1 carat diamonds, and I think they're about $1,000 a piece just for the diamonds. Yeah, just for the diamonds. But if you get a 2 carat diamond, is it $2,000?
Yeah, it's like 3 or 4.
It's probably like 3 or 4. If you get a 4 carat diamond, now this table says it's how much?
And it needs
29.
money.
That is a cheap 4 carat diamond. 4 carat diamond's like pretty big. I think it jumps up to like, oh, I'd say 6,000 to 8,000. Okay, Christina's helping us out. She's got some experience. Yeah, I'd say at least like $8,000 for a good one. So it's not linear. Let's graph it and see what we think. So put it in there. You putting it in there, Logan? Go through it.
Okay.
No, it's in the book. Yeah.
Okay.
So these must be like flawed, crappy diamonds. That's what I'm thinking. But even these diamonds, are they going to be linear? I don't know. We're betting not.
No, it's not quite right.
Yeah, if you look at the difference, goes up 1, changes by about 400, then goes up 1 more. Now it's changing by 600, then 1 more, changing by about 800. It's not linear. I still don't think it's accurate, but whatever. Zoom 9. Okay. I better erase that stuff. Okay, now I think this is a good example of the fact that data can be misleading. So, well, the last time we do this year, we'll probably be a little bit more careful. Look at that though. Do you guys think that just looking at that, you might be tempted to say it's a line?
Yeah. Not really, though.
Can you see curvature?
Yeah.
Yes.
If you see curvature, you should probably think not a line. Now there's a way in stats to make another graph with this. We change it around and do something else, and you clearly see this is not a line. The scale is making it hard to see, but if you look carefully, I think you'll see it's a curve. So again, I think we could try quadratic or exponential. They're probably both decent. Let's just do exponential, because diamonds grow exponentially. I just know that. So use the context. Think about that too. Let's just do the exponential one. So stat calc.
5.
I don't remember which number it is.
Zero.
Yeah.
0.
0. Exponential. X range.
Okay, so once you've got your model, what we're going to do this time is we're going to interpret r squared in context. This is something we do in stats pretty often. So we're going to do it here too. So here's our conclusion. Let's talk about our model a bit. Our model let me see. What?
The way the 0.30 to 0.75 is between 1,000.
Between how much weight?
0.30 and 0.75.
Yeah. Bad data. Someone made that up. I'm going to say this. I'm going to say 99.6% of variation. What do I put next? This is key. In y or x? Think about it. Your model's trying to explain the y's, right? So 99.6% of variation in the y's. You can't do this backwards. And what are the y's in this case? Put it in context. This is what I need to see on a couple of your problems. So 99.6% of variation in diamond price can be explained by variation in what?
Carrots.
In weight, which is carrots. On Bugs Bunny carrots. Okay. Can be explained by variation in carrots by our exponential model. So from that statement I can say, wow, that's a really good model. 99.6% crazy.
What's the 0.4%? What's the variation?
That's variation it can't explain. So in other words, it's not perfect. Okay. All right, so what is our model? We should write it down. It's y equals 814.96 times
379 to x. And also we put in y equals 2,325. Because that's what you're trying to find.
Yes. So then I think they said use the model to make a prediction. It said, did they give you a price or a?
Yeah, it is $2,325.
So they said how much does a diamond that costs that much weigh? So that cost goes which place?
Cost goes to y or
Y. Notice this was Y. This was X. You can really even write those as different things than Y and X. I don't emphasize that in this class a lot. But so we're gonna put in how much, Nick? 2,000.
325.
We're going to put that in for y. We've got a little equation to solve.
So you could do that in one. Yeah.
This isn't bad. Help me out. Solve for x. You said this bunch. First step, what should I do?
X log.
No.
Bring the x
Let's
down.
just get rid of the 814 first.
Divide by 8.
Divide. Good.
0.9.
You can use your calculator to get that. I'm just going to leave it alone. Just logarithm it right now. So now log it. I'm going to use the natural log. Okay, pull that x down. So I have the natural log of junk. That's really the way you should think about it. Whatever that is, it's just a number, whatever. Equals x natural log of 1.379. And then last step, what do I do if I want x?
No.
Those are numbers. There's no eating it because you're not trying to get inside. It's good. What's this doing to x?
It's taking the.
It's multiplying. It's not taking the x isn't in there. It's not taking the natural log of x. It's multiplying by x. So you divide. That's why you really need to ask yourself, what are these things doing to your variables that you want? If x is inside, you're going to have to do something totally different than in this case. Okay, and then you put that in your calculator to look up the answer.
It was about 3.26 carats is what I got when I did I graphed it
You graphed it.
and then had calculate an intersection.
You can do it that way too. That's fine, dude. Let's see if we do it in the calculator. You guys help me. Put it in your calculator, make sure you can do it. Remember, if you want that fraction, you go alpha y equals.
That's right. Dang it. Need this calculator. See, I got that.
Mr. McGee. Just enter it just like that. It doesn't matter.
Calculator, you know. No longer friends.
Can't do
with
that.
our friendship. You have to do that, right? You have to do that.
Oh, yeah.
At a steady rate. And then divide by 2.
And divide by 2.
Oh, that's so cool. Yeah.
Okay. So let's put that back in context. A weight of about 3.262 carats. Make sure you put your units in there. Will cost $23.25. It's just an estimate, right? It's not exact. It's just our model's estimate. Okay, we'll do one more tomorrow. Maybe we'll do a log regression, something different. Here's what you guys have. So I only gave you like 4 of them from the book, and then the worksheet has an additional 5, so it's about 9 problems. It'll take 1 or 2. So you've got about 9 problems total. That'll be due Wednesday, I believe. Okay, so tomorrow you'll have almost all in class to work. Maybe we'll do one more example, but
Like it's due Wednesday, and then we're just like, all right, turn it in tomorrow. Everyone's like, oh, we got half done. No, let's see what